Okay, last time we introduced ordered pairs of sets. Of course, there was some peculiar construction for these pairs, but the main idea is that based on such a construction, we may prove that two pairs are equal if and only if and only if their respective coordinates are equal, that is, x equals a and y equals b. Then we have then we considered so-called Cartesian or direct product of two sets, a times b, a multiplied by b, which is, informally speaking, just the set of all pairs where the first coordinate comes from a and the second one comes from b. And in fact, this machinery allows us to model in set theory, to model any, not any of course, but to model most binary predicates. So earlier we saw binary predicates of various forms, various properties of two elements, say x divides y, or I don't know, x is less than y, or whatever. So, and now we want to model such predicates in set theoretic context. How should I do this? In fact, the main idea is as follows. Instead of considering a predicate, I want to consider the set of all pairs of arguments which satisfy this predicate. So not the property of x and y satisfying 5, but just the set of all pairs x and y that satisfy phi. This is the main idea. So what I need here is the set. What I need here are sets of binary, arbitrary sets of ordered pairs, not necessarily products, but arbitrary sets. So I want to give the following definition. We say that R is a binary relation, between A and B if, and only if, of course, A is a subset of A times B, of A multiplied by B. So a binary relation is an arbitrary set, an arbitrary subset of the Cartesian product of A and B. Let's see some example. Let A be, say, 1, 2, the square root of 2, 3. And let B be 0, 1, 5. So I may consider the following set of pairs are 1, 0, 1, 1, 2, 5. What else? 2, 0, let it be the square root of 2, 0, and nothing else. So this is a set of pairs where each pair belongs to A times B. Clearly, this is a binary relation between A and B. Is it clear?
Yes.
Of course. For every binary relation, I can define 3 sets closely connected to it. The first set is so-called domain, the domain of our relation A. The domain of A is just the set of all possible first coordinates. So I can take all x's, where from? From A, of course, all x's from A, so that for some y, the pair xy belongs to A. So this is the set of all first coordinates. Okay. What is the domain of this relation A? So please.
1, 2, square root of 2.
1, 2, and the square root of 2. Of course, these are just the first coordinates. Clearly, this set, by definition, of course, is a subset of A, because I take just some elements of A. And dually, I can define the range, or sometimes they say codomain, but I won't avoid such words. The range of A is just the set of all elements from B, all points from B, such that for some x, xy belongs to A. So this is, of course, clearly a subset of B is the set of all second coordinates. And here we have 0, 1, 5, of course 0, which has been already mentioned. The range of A consists of 0, 1, and 5. Is it clear?
Of course.
Yes, it is.
Yes.
Clearly, every binary relation is a relation between its domain and its range. So, in fact, with some more effort, it is possible to get rid of this part of our definition, the binary relation between A and B. We may throw away this A and B from the definition, but this would require from us doing some abstract things, so let's don't do it. And also, the third set, I can consider the union of the domain and the range of A, which gives me so-called field of relation A. What is the field? The field is a set of all points, everyone, such that everyone is either the first or the second coordinate of some pair from A. That is, this is the union of the domain and the range. So clearly here, the field of A is just the set of first and second coordinates taken indiscriminately. So 1, 0, 2, 5, square root of 2. That's it. Okay. For every finite binary relation, I may, at least in principle, draw a so-called diagram. Diagrams, despite being informal, are very useful. What is a diagram? The main idea is as follows. You may depict every pair from A as an arrow, where its beginning point is marked with the first coordinate and its ending is marked with the second coordinate. So this arrow corresponds to our first pair. For the second pair, where the beginning and the ending coincide, I may use a loop. So then let's depict the pair 2, 5. I will have such an arrow. What else? And also this pair. Is it clear?
Yeah.
So
Yes,
formally, when taken formally, a diagram is almost the same as the relation itself. But there is no need to go formal here, because diagrams are something auxiliary. So you don't want to treat them too formally, but just use as an illustration for illustrating purposes. Okay. And now let's continue our definition. We say that R is a binary relation. I will, by the way, usually omit the word binary, for we don't want to consider any other relations in this course. R is a binary relation on A, on the set A, if and only if R is a subset of A times A. So it is the relation between A and itself. So let's give an example. The most interesting example here, the most important one, is as follows. For every A, I may consider the so-called identity relation. Identity relation is just set theoretic model for equality. The identity relation on A consists of all possible pairs X of the form XX for each X from A. So that it is a set of all pairs where the first coordinate equals the second one. So let's see what it is. 1, 2, 3. What is ID of A?
1, 1, 2, 2, 3, 3.
Of course. By the way, it has as many pairs as there are elements in A. And if I want to construct the diagram, it will consist of just loops. A loop at every point. Is it clear?
Yes. Thank you.
By the way, there is no need in thanking me every time. Okay. Also, let's consider some degenerate examples of binary relations. You know that the empty set is a subset of any set. Hence, the empty set is a binary relation, between A and B for whatever A and B. And also, the set of all possible pairs, the Cartesian product is also a relation. I think it is quite clear. And now, let's return to the case of a relation on some set. We will consider the following example of it.
Excuse me. Is there any identity relation with the empty set?
Okay, what is the identity relation on the empty set? By definition, it is the set of all pairs where X belongs to the empty set. Or formally, it is the set of all Z from this set, whatever it is, such that for some X, Z equals X, X, and X belongs to the empty set. Clearly, this condition is false. Is it clear?
Yes.
Hence, the whole condition is false as well. So, this is the set of all elements which satisfy some impossible, some contradictory condition. That means that this set is empty,
Not valid.
as it can't have any element. It has no element, so it is empty. Of course, the identity relation on the empty set is just the empty set. Is it clear?
And does it have any diagram? We shouldn't draw
Can
anything. because
we draw a diagram? Of course we can. So it is drawn here. No elements, no arrows.
Yes.
Okay. And now let's consider another example of some infinite relation. Let's take the set of all natural numbers as our A, and let's consider the following relation on A. Less than. We are already familiar with this thing as a binary predicate, and also let's see it in some set theoretic perspective. From the set theoretic point of view, this is the set of all pairs Mn taken from n squared, pairs of natural numbers such that M is less than n. We hereby assume that we have some definition for this thing, or at least some understanding of it. So less than is a set of all pairs where the first coordinate is less than the second one. Say, I may say that 2, 3 belongs to this relation. Do you agree?
Yes.
And what about 3, 2?
No.
Does it belong?
No.
No, it doesn't. It doesn't, for it is not the case that 3 is less than 2. And what about 3, 3?
No.
No, it is not an element. Okay, so this relation is, of course, infinite. So what does it give us? This gives us the possibility of treating our relations, our binary predicates, as sets, and then applying to them various set theoretic operations. For example, you can likewise define greater than, less or equal than, and so on. And then, for example, you may pose the following question. What is the intersection of two binary relations, less than and greater than? What is the intersection?
Equality.
Equality? No, no way. Because what does it mean that xy belongs to this 2? That means that xy belongs to less than and belongs to greater than. That means that x is less than y and x is greater than y. Is it possible?
No.
No. So this set is empty. There is no such pair. Is it clear?
Excuse me, how did you translate x less than y from x and y instead of less than?
Because this set, by definition, consists of all pairs where the first coordinate is less than the second one.
Oh, yes. Thank you.
This is just another way to say the same thing. Okay. And by the way, what is the intersection of these two identities? Less or equal and greater or equal. What does it mean that x is less or equal than y and x is greater or equal than y?
Is equal to y.
Yes.
Of course. So this is just the identity relation. The set of all pairs of identical elements. Is it clear?
Yes.
Okay. And now let's consider some specific operations for binary relations. Okay. Let A be some relation between A and B. Then we define so-called the converse relation. The converse, not inverse, for it is not an algebraic inverse under composition, as we shall see. But anyway, the converse of A. Some people yet say the inverse. The converse of A is the set of all pairs xy from A, from B times A, such that, so any ideas? Let's check your intuition.
Y is belong to
Yx
in
belongs to A, of course, of course. The main idea is to overturn every pair. So if we have, say, A, which consists of pairs 1, 2, 2, 2, and say 2, 3, then what is the converse?
3, 2.
2, 1,
No.
2, 1,
Okay.
2, 2,
2,
3,
2, and 3, 2. And diagram-wise, diagrammatically, on
The
a
arrows
diagram,
change their place.
of course, of course. Here, if these are arrows for A, if I want to obtain arrows for the converse, I have to change the direction of every arrow. And here, for the loop, of course, changing the direction means nothing. But anyway, so this way I can obtain the pairs for the converse relation. Is it clear?
Yes.
Okay. By the way, this notation is somewhat too complicated. We know that instead 2, 3 belongs to less than, we usually write the following symbol. 2 is less than 3. And let's do the same thing for an arbitrary relation. So we will say that x are y if and only if the pair xy belongs to A. This way, we may save 4 symbols. Is this notation clear? XY means just that XY belongs to A and nothing else for every binary relation.
Clear.
Okay. And now let's see what is the converse of the relation less than. What is the converse of the relation less than?
Greater or equal?
No. No. It is just greater. You know, what does it mean that xy belongs to this relation? This means that yx belongs to less than, that is, y is less than x. That is, x is greater than y. So xy belongs to greater than. We see that xy belongs to this one if and only if it belongs to this one. So the converse of less than is just greater than. And what is the converse of greater than?
Less than.
Less than, of course. And in general, the converse of the converse is the original relation. So let's prove the following lemma. Okay, lemma 1 says that for every binary relations P and Q between whatever sets, the converse of the converse is what?
P.
It's just our original P. And what is the converse of the union? You know, relations are sets, so we may apply set theoretic operations to them.
P inverse and Q and
No,
intersect of
no,
Q.
no. Union. The union. So this operation is monotone. For a greater set, for a greater relation, the converse is in general greater. So let's prove it. For the first, I want to prove that these two sets have exactly same elements. But I know that every element of either set is uniquely expressed as a pair. So, to spare some formal work, I may consider only pairs. What does it mean that some pair xy belongs to this set? This is equivalent to that yx belongs to the converse of P, which is equivalent to the fact that xy belongs to P itself. So I see that every pair is an element of this set if and only if it is an element of this one. As every element of either set is a pair, that proves that these sets have the same, exactly the same elements. That is, these two sets are equal. Is it clear?
Yes.
And the same procedure for the second case. What does it mean that xy is an element of this set? That means that yx is an element of the union. As it is an element of the union, that means that either yx belongs to P or yx belongs to Q. But this is equivalent to the following. xy belongs to the converse of P. And here, xy belongs to the converse of Q. That is, xy belongs to either the converse of P or to the converse of Q, that is to the union. So I see that these two sets have exactly same elements, so they are equal. Is it clear?
Yes.
Okay. Okay. By the way, what is the converse of the empty set?
Empty set.
Of course. If you have no pair, here, then after conversion you will still have no pair. And another operation on relations, which is a little bit tricky to define, is the composition. Let P and Q be some binary relations. Let's define the following. The composition of P and Q in this order. The composition of P and Q, which is written second, acts first. So what is it? Formally, this is a set of all pairs x, z, where x comes from the domain of P and z comes from the range of Q, so that there is some intermediate point y such that x, p, y, and y, q, z Diagrammatically, that means the following. I say that X and Z are connected by a composition arrow, that is, this pair belongs to the composition, if and only if there exists some intermediate point such that there is a path going via that point from X to Z and consisting of two arrows. First P arrow, then Q arrow. So informally, I say that XZ belongs to this composition if and only if there is a two arrow path from X to Z, first going Y or by P, then by Q. So that means that you may say, let X and Z be some cities, and P means that it is possible these cities are connected by plane, by a plane flight, and Q means that they are connected by a train ride. So it is possible. What does it mean that XZ belongs to the composition? That it means that it's possible to go from X to Z, say first by plane, and then after having a change at some point Y, then by train. Is it clear? Or is it too abstract?
Can you give us an example, please?
Okay. Let's see some examples. First, let's consider, say, the same relation as we have already seen, 1, 2, 2, 2, and 2, 3. What is the composition? Or here is the diagram. What is the composition of this relation with itself? This is a set of pairs which are connected by a two-arrow path. A two-arrow path.
1, 2, 2 and 1.
1 and 2.
1,
Of
2.
course, 1 and 2 are connected by a two-arrow path. Why? Because there is an arrow from 1 to 2, and there is an arrow from 2 to 2. These are connected by a two-arrow path. Also, 1 is connected to which point? By a two-arrow path.
3.
To 3, of course. Of course, to 3. So 1, 3. What about 2? 2 is connected to 2 by a two-arrow path. Why is it so? Because you may traverse this loop twice or thrice or how many times you want. And also 2 is connected to 3 by a two-arrow path. First you go from 2 to 2, then to 3. And 3 is connected to no point. by a two arrow path. Is it clear?
Yes.
So the main idea here is to find two arrow paths, but in general, these paths are such that first relation is P and the second one is Q. By the way, it is clear that if P is a relation between A and B, and Q is a relation between B and C, then our path first leads us from, by P, it leads us from A to B, and then by Q, it leads us from B to C. So that means that then the composition is a subset of A times C. Exactly because the domain of P is a subset of A and the range of Q is a subset of C. Is it clear?
Clear.
Another easy observation is as follows. Why so strange notation? Why do I write P at the second place when P comes first? When P is in the second place? The main idea is to be in a good accord with the composition of functions. Are you familiar with the composition of functions? If G and F are two functions, what is their composition?
G of fx.
This is a function which returns G of f of x at each point x. Is it clear?
Yes.
You see that the second one acts first, and then by G you go to this point. Is it clear?
Yes.
We want that our functions are binary relations of some special form. So if we want to keep this nice and at least familiar equation, we need this strange convention when the the relation written second acts first. It is strange, but that is. Okay. And now, let's prove two theorems about composition. Both are very important. The first theorem deals with the associativity of composition. So it is the associativity law. The associativity law for composition. For every three relations P, Q, and R, for every three binary relations, this composition equals this one. So it doesn't matter how I group them with brackets. Let's prove it. As usual, we will take some arbitrary pair and prove that it is an element of the left-hand side if and only if it is an element of the right-hand side set. Assume that It is so. What does it mean? Let it be not Z, but W. That means that there exists some Z, some intermediate point, such that there is a path with a change at this Z, so that X and Z are connected by an arrow from this relation, and ZW are connected by an arrow from A. This is exactly by definition, nothing else. From X, I go to Z by this one, and then by A, I go to W. Is it clear?
Yes.
Okay, and now let's unfold this term. Let's unfold it according to the definition of composition. What does it mean? That means that there exists some intermediate point Y, such that from X I may access Y by P, and then from Y access Z by Q. Here it is. Is it clear? Clear or not?
Not too clear.
But what is the problem? Was this one clear?
Mm-hmm.
But what is the problem here? I have just unfolded this part. What does it mean? That means that there is a two arrow path from X to Z. First by P, then by Q. What's your question? What is not clear?
Now it's clear. Okay.
Okay, and now let's do some logic. Of course, our natural logic. First of all, does this thing depend on Y?
Yes, it does.
No, it doesn't depend on Y. So my idea is as follows. I want
So it is
to
W?
Z and W. No mentions of Y.
Oh,
So I want to move this Y out of these brackets. It's logically correct, in fact, because this thing does not depend on Y. You may say something. There exists Y such that Y is even, and say today is Thursday. Why this statement is true? It is true if and only if there exists some Y such that Y is even and today is Thursday. Don't you agree?
Yeah.
This thing just does not depend on Y. So this one is true when? When there is an even number and today is Thursday, as well as this one. So they're equivalent. And this is a general logical law. So I may move this quantifier out of the bracket. X, P, Y, and U, W. So that W. Then I know that there exists Z and there exists Y. They equivalent to there exists Y and there exists Z. And here I may regroup the bracket the following way. As conjunction is associative. Do you agree?
Mm-hmm.
And now let's look at this thing. It does not depend on Z. It does not depend on Z. That means that I may move this quantifier here because this thing does not depend on Z. So I will have the following. There exists Y so that X P Y and there exists Z such that Y Q Z and Z R W. Ha! But this thing exactly says that there is a path from Y to W first by Q, then by R. So that means that there exists some Y, so that X, P, Y, and the pair Y, W belongs to the composition of Q and R. But this one in its turn means that there is a way from X to W, first going by P and then by my composition. So I have that this pair XW belongs to this relation if and only if it belongs to this one. So these two, whatever grouping of terms I prefer, these two are equal. Is it clear?
Yes. Yes.
Maybe I can try more informal, less formal explanation. So what does it mean? That means that there is a way from X to W going through some Z from X to W. Where this pair ZW belongs to R and this pair belongs to this composition. But that means in its turn that there is some Y with such a property. But then I may look at these two arrows and conclude that there is a way from Y to W going first by Q, then by R. So I have the following way from X to W first by P, and then by Q composition R. So that means that my pair X Z XW, excuse me, must belong to this composition. If it belongs to this one, then it belongs to this one as well, and vice versa. Is it clear?
Clear?
Okay. So the interesting thing. And what about any connections between composition and conversion? Theorem 2. The converse of the composition. What is the converse of the composition? What is it?
The composition of Q and P.
Of Q and P? Really? And what about conversions? This is the composition of the converses, but the order also changes. First, let's see it on a diagram. What if there is some arrow, say xz? What does it mean that xz belongs to this relation? That means that there is a path from z to x, first going by p, and then by q. It means that there is some y, so that z p y and y q x. And what about x and z? That means that there is a q converse arrow from x to y and a p converse arrow from y to z, which results in an arrow going first by q converse, then by p converse from x to z. So if xz belongs to this one, then xz belongs to this one, and vice versa, of course. Let's rewrite it in formulas without drawing arrows. Okay, the proof. For every pair xz, this pair belongs to this set if and only if zx belongs to this one. By definition, that means that there is some y, so that z p y and y q x. And now let's overturn these pairs. Y p converse z and x q converse y. Let's change the order in the conjunction, which is logically equivalent. X q converse y and y p converse z. And now I see that there is a clear path from x to z, first by q converse and second by p converse. So these two are equal as they have the same elements. Is it clear? Is it clear or not?
Actually, I was
Yes.
disconnected this time. Sorry.
So what's your question? What is your question?
No, I was disconnected and I have to rewatch this part,
I see.
unfortunately.
I see. In fact, all these things are written down to my lecture notes. So it's not too bad if you missed something. Okay. But did you have matrices in your algebra course?
Yes.
Do you know what is the matrix transpose? The transposed matrix, what is it?
We changed the row by the
Of
column
course.
indices.
And what is the transpose of the product of two matrices?
I think it's B transpose times A transpose.
Of course. And this is the same as we have here. The same. So there is some algebraic similarity between conversion of taking a converse of a relation and transposing a matrix. There are some similarities. And also, the transpose of the transpose is the original matrix. And the same, of course, for the converse, as we have already proved. But you know, what was your sign for unary matrix? For unary matrix? Or identity matrix? How did you denote it?
With I.
The same as
With I?
In the indices.
yeah.
This way.
Yeah.
It doesn't matter, the index. Okay. So, but is this true? A multiplied by the transpose equals the identity matrix. Is it true in general? Of course not. Of course not. So that means that our transpose is not an inverse for multiplication. And likewise, this conversion is not the inverse for the composition. Namely, we have the following. Like the matrix case, here we also have neutral elements. We have some identity relation. Let's prove the following lemma. It's very easy. Let R be some relation between A and B. Then if I take such a product, that is such a composition, ID, the composition of ID A and R, I'll obtain what? What if you take the composition with identity relation?
Would be the relation, so.
Of course. And likewise, you will have the same R. How is it possible to prove it? Let's prove just the first equation. It's really easy as usual. What does it mean that xz belongs to this composition? That means that there exists some y, so that xy belongs to the identity relation and yz belongs to R. But what does it mean that xy belongs to the identity relation? That means that x equals y. So you see the following strange statement. There exists y, which equals x, and y are z. But you know that equal sets behave identically. That means that if y first equals x and then there is an arrow from y to z, that means that there is an arrow from x to z. Is it clear?
Clear.
And vice versa. If x are z, there indeed there exists such y. What should you take as y? Which element will both exist? Will both equal x and have an arrow from it to z? If x are z, what should you take as y?
X.
Of course. If you take x as y, you will obtain just this thing. So xz belongs to this composition if and only if xz belongs to R. So R equals this composition. That means that my identity relations are similar to identity matrices, to unary matrices. But the conversion is not an inverse in the following sense. Let it be an exercise. By the way, it is very easy. An example. We say that there exists such A, so that A composition, the converse, let it be, say, a relation from on A, is not the identity relation. It's very easy to see why is it so. For example, let's R be as follows. 1 from 1, let's go to 2. And also to 3. So R is just 1, 2, and 1, 3. What is the converse, by the way?
2, 1, and 3, 1.
2, 1, and 3, 1. And now I say that there is an arrow by the converse relation from 2 to 1. Do you agree? So just see. I may reach 1 from 2 via a conversed. And then from 1, I may go to 3 via A. That is 2, 3 belongs to this composition. Is it clear?
Clear.
But of course, this pair does not belong to ID, as 2 is not equal to 3. So ID and this composition are not the same. Is it clear?
Clear.
And the last concept I want to consider today is so-called image. So the image of a set under a relation. What is the image? Assume we have some binary relation between two sets, A and say B. Here we have some point which has an arrow here, also here, and say here. And also let be some more points. What if I take some set X which has two common points with A? I'm interested in the following. I'm interested in the ends of the arrows which begin in X. So which are the ends of these arrows which begin in X? The ends are just these points, but not that one. Is it clear?
Could you please repeat again your question?
So
What arrows begin?
I'm interested in the endings of arrows which begin somewhere in X. So I want to consider the set of points which are accessible from X. Why are the set of R accessible? The set of R accessible points from A, from X.
You mean those two green points?
No.
No.
The blue one.
The endings of arrows which begin in green points. Blue.
Yeah.
Blue one. Formally, it is as follows. Let, as usual, R. So it's not needed. Formally, this is a set of all elements of the range of R such that they are accessible from some point from X. Formally, it is just that. These are exactly such points from the range where to I may go from some point of X. Is it clear? Okay, let's have an extended example. Let R be 1, 2, 1, 3, 3, 5, 5, 8, 2, 0. Let it be, say, 2, 1. So, and X, what is the image? By the way, this is called the image. The image of X under R. What is the image of the set 1, 5, 2? Which points I may access starting from 1, 5, and 2? From 1, I may go where?
2 and 3.
From 5?
8.
And from 2?
2, 1.
From 2 to 1. So, I can access just 2, 3, 8, and 1. And this is the image of my X under A. So these are just the endings of arrows which begin at some point in my set. Is it clear?
Yeah.
Obviously, this set is a subset of the range. It is a subset of the range of A. What if I take the image of the whole domain of A? What is it? Which points I may access from the set of all starting points of A.
Range for R?
The range, of course, the range. This is just the range. The whole range. And likewise, as well as the image, I have a pre-image. The pre-image. The pre-image. The pre-image under A is the same as the image under the converse relation. That is, I can consider the pre-image as the image under the converse relation. So I have to consider all points A. Where from? From the range of the converse relation, so that there exists some B. Where from? From X, of course, such that there is an arrow from B to A. But what is the range of the converse relation, by the way? Where the converse arrows end?
The DOM of R.
Of course. So this one equals to the set of all elements from the domain, such that for some B from X, I have an arrow from A to B. So informally, the pre-image is just the set of all points where from some point in X is accessible. This is, of course, a subset of the domain. And clearly, the pre-image of the range is what?
Domain of R.
And what about our example? Let's say consider the pre-image of the following sets, say 2, 5, and 9. What is the pre-image of this set? I want to consider the beginnings of first. First, I want to find any arrow with the second coordinate being 2. Is there any? Is there an arrow coming to 2?
One.
There is such arrow. Is there an arrow going to 5? and going to 9? No. And what are their beginnings? The first coordinates. These are exactly 1 and 3, so it is the preimage. Is it clear?
Can you repeat it again, please?
Repeat what? I want to find the preimage of this set. That is, the set of all points where from at least one point from this set is accessible. Where from 2 is accessible? What are the beginnings of arrows ending in 2? We have exactly one arrow ending in 2. Its beginning is 1. We have exactly one arrow ending in 5. Its beginning is 3. We have no arrows ending in 9.
Clear. Thanks.
So the main idea is where can you go from these points, or where from can you come to these points if it is the preimage. Just change the direction. So this is a set of all points accessible by R from any point in your set X. Formally, this is exactly such for image. The set of all elements from the range, so that there is an arrow from X going to this point of our range. By the way, let's compare it to the definition of the range itself. The range of R is the set of all points from our B such that there exists A, so that A are B. So the image is just a restriction of our range. So we here are to take not all points which are second coordinates, but just those of them which are second coordinates of any point from X. Is it clear?
Clear.
So, at the seminar, you will have to prove some general properties of images, preimages, compositions, and so on. By the way, let's take another example. Say, let I be 1, 2, 1, 3, 5, 2, 6, 7, 8, 3, and that's it. So, what is the image of the set 0, 1, 6 under R? Which points are accessible from 0, 1, and 6?
1, 3, and 7.
Really, 1 is accessible.
No, 2, 3, and 7. Sorry.
First of all, you see which pairs have their first coordinate in this set. It is just this pair, this one, and this one. And then you will take the respective second coordinates, which are 2, 3, and 7. And we have no pair with the first coordinate being equal to 0. And now, what about the preimage? Let's consider the set that consists of 2, say 3, and 9. Let's take all the pairs with the second coordinate belonging to this set. Which pairs lead us to this set? 1, 2. What else?
5, 2.
1, 3. What else? 5, 2. And 8, 3. And 8, 3. So 4 pairs. And now, what are their first coordinates? 1, 1, 5, and 8. So this set is accessible from points 1, 5, and 8. Is it clear?
Yeah.
A few words about geometrical interpretation, about possible geometrical interpretation. Do you agree that our plane might be considered as a set of pairs of coordinates?
Yes.
In fact, any geometrical figure is a binary relation. Let's consider, for example, such figure F. F is a subset of the plane. Hence, it is a binary relation. F is a binary relation on R. Every geometrical figure is a binary relation. What is the domain? The domain is the set of all x's. You know that x belongs to the domain of F. If and only if there exists some y such that xy belongs to F. So geometrically speaking, the domain is what? What is the domain? What is it? It is just the projection of our figure to x's. Just the projection. Is it clear? And what is the range? What is the range?
The projection to y.
Is it clear?
Clear?
Any questions?
No?
No.
Okay, thank you.